We are going to start with lecture 4 of chapter Introduction to Sets. So in our previous lecture, we have discussed subsets and supersets. Then we have seen what are universal sets and power sets. Then we were talking about Venn diagrams, and finally we have talked about the intervals, that is the subsets of R, the real numbers R. Now in this chapter we will talk about the definition of complement of a set, union and intersection of sets. Then we will talk about the symmetric difference of sets. So we start this chapter with the definition of complement of a set. So suppose we are saying U is the universal set. If we are talking about the Venn diagram, we are saying U is the universal set, and let A is a subset of U. The subset of U, they are represented with A. This is A is a subset of U. Then the complement of A, denoted by A dash, or we are writing it is U minus A, is defined as A dash is equal to, we are talking about the complement of A, that is all x in U. First thing, what are the elements of the complement of A? They are all elements of the universal set which are not the elements of A. So we are saying, if this is the set A that we have, this portion I am saying, this is the set A, then complement of the set, it is this region, the region of U which is outside A, or these are the elements of U which are outside, which are not the elements of A. So we are saying that an element X, it belongs to A complement. It means we are saying an element belongs to A complement. This is implied and implied by that X does not belong to A. We are talking about all those elements of the universal set which are not the elements of the given set A. They are the elements of the complement of A. We are talking about, this is set A, the region inside. If we talk about the region, this is representing the elements of the set A. This region, it is representing the elements of U. So region of U which is not part of A, that is A complement. So let us consider an example to better understand the things. Suppose we are talking about the universal set U is given. It has elements 1, 2, 3, 4, 5, 6, 7 and 8. And the set A is given. It has elements 2, 4, 6 and 8. Let's try to understand with the help of Venn diagram. We are having the set A. It has elements 2, 4, 6 and 8. U has elements 1, 2 is already included, 3, 4 is already included, 5, 6 is already included, 7 and 8 is already included in U. When we are talking about U has 1, 2, 3, 4, 5, 6, 7 and 8. What are the elements of A complement? Those elements of U, we are talking about those elements of U which are not the elements of A. 2 is element of A, 4 is element of A, 6 is element of A, 8 is element of A. The remaining elements of U, 1, 3, 5, 7, this is the set A complement. Now suppose I am talking about, this is the set A complement, this is the set U we have, this is A, and we are writing A complement. The elements we obtain, it is 1, 3, 5 and 7. Now suppose again I find the complement of this set A. Suppose I find the complement of the set A again. This set A complement is there and we are finding the complement of this set. Now what we are doing? The elements we are removing over here, 1, 3 is already there, 5 is already there, 7 is already there. What we obtain? We are left with this 2, 4, 6, 8. This is same as the set A. So this is the standard result. This is not the formal proof. We will discuss the formal proof in our later slides. You can just understand this result, that if we are talking about complement of A and complement of this whole set, we will again obtain the set A. So this is our first result related to the complements. So we are saying that the complement of a set is the set itself. Complement of the complement of a set is the set itself. This is our first result related to complement of a set. Let us consider another example. If n is the universal set, n over here it represents the set of natural numbers. A is the set of all elements, all natural numbers that are odd. So what is the complement of this set? We are saying set of natural numbers we have, it is 1, 2, 3, 4, 5, 6 and so on. The set A that is given to us, it is all natural numbers that are odd, 1, 3, 5, 7 and so on. What is A complement? We leave these elements 1, 3, 5, 7 and so on. What we are left with is the elements 2, 4, 6 and so on. And we can write it as it is x, such that x is a natural number and x is even. So we are left with only the even natural numbers. So this is the set A complement that we have. So we have listed certain properties over here. We are not going to talk about the proofs right now. Just as we have studied the property that the complement of set A is A, similarly we have these properties. So if we are talking about the complement of the universal set, U is the universal set. I am talking about complement of the universal set. We are saying this is the set U. What is the definition of complement? We are saying it is all those elements of U such that X is not in the universal set. So is there any element which is in the universal set and which is not in the universal set? There is no element over there. So we are saying that this set is an empty set. The complement of the universal set is a empty set. Next is the complement of the empty set is the universal set. We are talking about the complement of phi. We are saying X belongs to U, all those elements of universal set. X does not belong to phi. Is there any element which belongs to phi? There is no element. It means we are talking about all the elements of U. The answer we will obtain it is U. You can also look it in this form, that we are saying we have a set U that is a universal set. We are calculating the complement of this set and we are saying it is phi. Now if I will take the complement of this set again, if I will take the complement of this set, I will take the complement of the set phi, I will obtain the universal set, because complement of the set is the set itself. In some cases we can also write the complement with C, or we can represent the complement of a set U with this dash over there. So it is up to you that how you want to represent. So you can use either of these two notations. Next we have is, this is our first thing related to sets. Next is the operations on sets. The next operation we have, it is the union operation. So suppose we are talking about two sets A and B. The union of these two sets is another set that contains elements of A, that contains elements of B, or the elements common in both of them. So how union is defined? We are saying that we are having two sets A and B. Union is written as A union B. This is the symbol for union. A union B, it is a set. A union B is a set. What are the elements of this set? They are all X such that either X is an element of A or X is an element of B or both. It contains all the elements of the set A as well as that of the set B. So let us consider an example over here. We are saying if A is equal to this set, it has elements 3, 4 and 5. B has element 4, 6, 8 and 10. Then A union B we have, it has elements, all the elements of A, 3, 4, 5, 6, all the elements of set B. Elements of the set B, 4 we have already listed over here, 6 we have already listed over here. There is no need to repeat the elements because it is a set. Repetition has no meaning over here. Then 8 and then 10. So these are the elements that we have for the set A union B. Next, let us try to understand in terms of Venn diagram that when we are talking about the unions, then what we mean by the union of the two sets. So we are saying that suppose we have two sets. This is the universal set we have U. We have two sets A and B. This is the set A. This is the set B. This is set A. This is set B. So this whole shaded region that we obtain over here, this is representing the union of the sets A and B. So what we can say, X belongs to A union B. We are considering any element over here. This is suppose we are saying this is X. When it is like this, we are saying this implies us, or this is implied by that X belongs to A or X belongs to B. When we are using this term or, what we mean to say, X can be over here, that either X belongs to A only, or X can belong to B, or X can belong to both. All the three cases we are considering over here. So we are saying when X belongs to A union B, this is implied by, and this implies that X belongs to A or X belongs to B. So it is important to note over here that when we are using this or over here, we are also including the condition or both. This case we are considering over here. Let us consider another example. So now two sets are given. One is the set A. It is A is the set that is X such that X is prime less than 10. It is a prime number less than 10. Then B is another set given to us. B has the elements all natural number. X is a factor of 12. B is the set of natural numbers such that X is a factor of 12, and we have to find the union of these two sets. We have to find the union of these two sets. Just wait a minute. So if we list, what we have to do, this is a set A given. So elements of the set A, we are saying X is a prime and it is less than 10. So what is the first prime number? The first prime number we have it is 2. One is neither prime nor composite. So elements of the set A, they are 2, 3, 5 and 7. Prime numbers less than 10. And what are the factors of 12? X is a natural number and factor of 12. Set B, we have it is 1, 2, 3, 4, 6 and 12. These are the factors of 12. Now we have to calculate the value of A union B. So they are the common all elements over here. So it is 1, 2, 3, 4, 5, 6, 7 and 12. All the elements that we have over here, we write a set. It has elements 1, 2, 3, 4, 2, 3 we have already considered, then 5, then 6, then 7 and then 12. So A union B, we are saying it is a set with these elements. Next theorem we have A union A complement, that is equal to U. What is the definition of A complement? We are talking about all those elements X such that X belongs to U and X does not belong to A. If I am talking about A union A complement, suppose I am talking about in terms of Venn diagrams, we are saying this is the set U, this is the set A, this region, this outside region is the set A complement, union of both these, that will be the complete set U. This is in terms of Venn diagrams. When we are talking about A union A complement, how we can write this set? We are saying it is by definition of union. We have to prove that A union A complement is U. We are saying A union A complement. How we prove equality of sets? We have to prove that one set is subset of other and second is subset of first. A union A complement, it has all the elements X such that X belongs to A or X belongs to A complement. This is by the definition of union we are saying. This definition of union we have already seen that an element is in union if X belongs to A or X belongs to A complement, or we are saying both these conditions they hold. So what this thing means? This thing means that X we have over here, it belongs to U. We are talking about all the elements from the universal set for which such that X belongs to A, or what this thing means? X belongs to A complement means X does not belong to A. And what is this set? We are saying all elements of the universal set which belong to A or which does not belong to A. There is no condition over here. What this thing is, what is the meaning of this thing? We are saying all X belongs to A or X does not belong to A. It means either X belongs to A or it does not belong to A. It has no effect over here. So what we are left over here is X belongs to U. It means we are left only with the universal set. It means that the union of a set and its complement, it is always a universal set. A union A complement is universal set U. Next we have is the representation of sets using union and intervals. We have already seen the intervals. Now we are going to talk about the operations on those intervals. We are talking about the set of all X such that X is greater than equal to 2 or X is less than minus 2. When we are saying X is greater than equal to 2, in interval form we are writing 2 comma infinity. X is less than equal to minus 2 means minus infinity comma minus 2. Let's plot this. 0, minus 2, 2. 2 is included. Dark dot over here. All these points. Then minus 2 is included and all these points. So what is the union of these two? What is the union of these two? We will just put the union sign over here. So we are saying the answer we have over here, it is interval minus infinity comma minus 2. This part I am talking over here. Union closed interval 2 comma infinity. So this is the union of the two intervals. Next, the set where x satisfies -1, we are talking about this is 0, -1, this is 3, this is 5. -1 is less than x is less than equal to 3. -1 is not included, 3 is included, all the points in between are included. Then it is written x satisfies this, or x is 5. 5 is included, there is no points in between, they are included. But how we can write this in interval form? This interval we can write open at -1 comma 3 closed at 3. Then this point we have, it is 5. This is the single element 5, single number 5 we are talking over here. So this is how we can represent -1 is less than x is less than equal to 3, or x is equal to 5. Next we have is in previous, this one we have done, this one we have done. Next we have is the intersection of sets. So when we are talking about two sets A and B, intersection, it is denoted by this symbol. We are talking about two, this is the universal set. We are talking about two sets A and B. This is the set A, this is the set B. And when we are talking about the intersection of these two sets, we are talking about this region, that is common region between A and B, or the points which belong to both A and B. So how we are representing? We are saying A intersection B, it means all those x such that x belongs to A and x belongs to B. When we were talking about union, we were writing x such that x belongs to A or x belongs to B. So the difference over here is we are using or, over here we are using and. So what is the difference? When we are saying or, it means either x belongs to A, x belongs to B, or both. When we are talking about A intersection B, it means we are talking about those points that are common to both A and B. So we are saying that A intersection B means x belongs to A and x belongs to B means only those elements are there which belong to both A and B. So if I am talking about the set A intersection B and I am saying that an element x belongs to A intersection B, what this thing will mean? That x belongs to A and x belongs to B. Conversely, if I am talking conversely, if I am saying that x does not belong to A intersection B, now where the x will lie? Again consider the universal set. We have two sets A and B. This is universal set, this is set A, this is set B. We are saying x does not belong to A or B. It means that except for this region, x can lie anywhere. Except for this region, x can lie anywhere. Now, how we can represent this portion. Suppose we are saying this is this circle, it is representing the set A. The region outside this set A, look at this region over here, which is outside the set A. If I consider any point in this region, I will say X belongs to A complement. Now, again, same case. I am drawing two circles over here. This is set A, this is set B. This is the common portion we have. Now I am considering the region outside B. I am talking about the region outside the B. And I am saying suppose a point is over here. Except for B, this point is over here. It means that X belongs to B complement. X belongs to B complement. What we have obtained, when we are leaving this portion A, we have covered this area. When we are leaving this B, we have covered this area. If I will take the union of, I am saying X belongs to A complement or X belongs to B complement. I am using OR over here. So basically I am talking about the union of these two regions. So what we are saying, X belongs to A complement. X is outside the A or X is outside the B. In that case, we are saying X does not belong to A intersection B. I am again trying to explain this. We are saying we have, this is the U. We have two sets. This is the set A and this is the set B. When I am talking about this is A and this is B, I am saying what is A complement? A complement is this portion. A complement is this portion. B complement, when I am talking about, suppose I am representing it with dots. B complement is this portion outside B. This dotted region I am talking about, this is representing the B complement. What is the portion that is not shaded in any of these two cases? It is this middle portion we are left over here. This is not shaded in both these cases. So what we are saying, that if I will consider an element X that belongs to A complement or B complement. Another way we can say X does not belong to A or X does not belong to B. It means that X lies outside this region. So this thing will mean that X does not belong to A intersection. So these two conditions we are saying they are equivalent. This is the converse of the definition that we have used for the intersection. This is the converse we have. So let us consider an example to understand the intersections. So we are saying the set A is given. It is X such that X is equal to 3n, n is an integer. B is X such that X is equal to 4n, n is an integer, and we have to find A intersection B. So what these sets they are representing? The first set is X is equal to 3n. It is representing the factors or multiples of 3. So if I will write the elements of A, these are n belongs to Z. So 0, 3, 6, 9, so on, minus 3, minus 6, minus 9 and so on. If I am talking about the set B, we are having it is 0, multiples of 4, 8, 16 and 12 and so on. On this side we are saying it is minus 4, minus 8, minus 12 and so on. What is A intersection B? What are the common elements over here? So the first common element, if I will write the next element over here, it is 12. Over here it is minus 12 and we are saying so on. So the first common element A intersection B, when I am saying, I am talking about the common elements. We are saying it is 12. It is minus 12. Next will be the elements like this. So what are these elements? These are basically the A intersection B. We are saying it consists of all those x. These are factors of multiples of 12. So we are saying it is 12 times n, and n belongs to Z. So this is the intersection of these two sets. Next is if A is a subset of U. Next thing we have to prove is that if A is a subset of U, we have to prove that A intersection A complement is 5. Again, consider the set U. This is the set A that we have. This is the set A. This portion we are saying this is the set A, and outside it is the set A complement. So when I am talking about A intersection A complement, so what is the definition we are going to use over here? We are talking about all the elements of the set U. We are taking intersection over here, A intersection A complement. We are taking all the elements from the universal set such that x belongs to A. It is AND over here, and x belongs to A complement. Is there any element such that x belongs to A and x belongs to A complement? There is no element. When we were talking about the union, A union A complement, we were having x belongs to U such that x belongs to A or x belongs to A complement. It was OR over here. So we are saying either x belongs to A or x belongs to A complement or both. Then we were saying that complete universal, any element of the universal set will satisfy this property. And now when we are talking about the intersection, we are saying x belongs to U such that x belongs to A and x belongs to A complement. It is AND over here. So is there any element which is present in both A and A complement? What this thing means? X belongs to A and x does not belong to A. A complement means x does not belong to A. Is there any element which belongs to A and it does not belong to A? There is no such element. So we are saying that this is the empty set. So A intersection A complement, it is 5. Next example. Give an example of 3 sets A, B, C such that A intersection B is equal to A intersection C, but B is not equal to C. This is just like the cancellation law. We are talking for the numbers. Suppose I am saying A into B is equal to A into C. If we are saying A is not equal to 0, what we can do? Cancel these terms. We obtain B is equal to C. If A plus B is equal to A plus C, we get B is equal to C. But we are going to prove that no such kind of result exists for the sets. That is, if A intersection B that is equal to A intersection C, it doesn't mean that B is not. It doesn't mean that B is equal to C. So what we can do? We can consider the set A has elements 1, 2, and 3. These are the elements of the set A. Suppose B has elements 3 and 4. And the set C we are considering, it has the elements 3, 5 and 7. These are the 3 sets we are considering. Now if we calculate A intersection B, what are the common elements over here? 3 is the only common element. The answer we obtain it is 3. If we are calculating A intersection C, the only common element we have it is 3. 3. Both these sets, they are equal. Now I hope it is clear to you why we have considered this set C in this one. So that when we calculate A intersection C, the answer we obtain, it should be equal to A intersection B. Now what happens over here? A intersection B is 3, A intersection C is 3, but clearly we have A is not equal, B is not equal to C. You don't want to consider this set, just consider this set. We can just consider it in this. We are considering B is equal to 3, 4, C is equal to 3. What is A intersection B? 3. A intersection C? 3. But B is not equal to C. So this is how we can prove this result. Next we have two terms. One is the intersecting sets and second is the disjoint sets. So two sets A and B are said to be disjoint if A intersection B, that is equal to 5. A intersection B 5 means we have a set A, we have a set B. There is no common element. If there is no common element between A and B, then we say that the two sets, they are disjoint sets. And if there is at least one element, their intersection, if there is at least one element that is common over there between A and B, then we say that those two sets, they are intersecting sets. In this case, if we will calculate the intersection of these two sets, we are talking about the intersection of these two sets, there is nothing common over here. So we are saying the set A intersection B, the common element, the set of common elements, it is empty. So A intersection B is 5. This is equivalent to the condition we are saying disjoint sets. If A intersection B is not 5, it is non-empty, then we will say that these two sets, these are the intersecting sets. These two sets, they are the intersecting sets. Let's consider another example. If A is equal to, A has the elements 1, 3, 5, 7, 9, B has elements 2, 4, 6, 8, C has elements 3, 5, 2, 3, 5, 7, 11. We have to find A intersection B and A intersection C. So what is A intersection B in this case? What are the common elements between A and B? 1 is there, 1 is not there, 3 is there, 3 is not there, 5 is not there, 7 is not there, 9 is not there, 2 is not over here, 4 is not over here, 6 is not over here, 8 is not over here. So we are saying A intersection B, it is empty. When we are calculating A intersection C, A intersection C, 1 is not there, 3 is there, 5 we are saying it is there, 7 we have common, 9 is not there, 2 is not there, 3, 5, 7 and 11. Why we are checking both ways? It is sufficient to check only once. We are saying if 1 is not present over here, then it is not present over here. To make myself double sure, I am checking both ways. There is no need to check both ways every time. Just to check whether I am doing it right or not, I am just checking it the both ways. So what we obtain over here is A intersection B is 5. It means A and B, they are disjoint sets, and A intersection C is not equal to 5. This is not equal to empty set. It means A and C, they are intersecting sets. They are not disjoint. They are intersecting sets. Next is these two sets, they are given. A has elements 2, 3, 5, 7 and 11, and B is the set 5. We have to find the value of A union B and A intersection B. So B is the empty set. So when we are writing A union B, we are including all elements of A, we are including all elements of B. The answer 2, 3, 5, 7, 11, that is set A. So what we have is A union 5, that is equal to A. We will see these results in our next slides again. When we are talking about A intersection B, what is common between A and B? B has no element, so there is nothing common between A and B. So we are saying that A intersection B, that is equal to empty set or null set, or we can represent it with phi. Next is give examples of the three sets A, B, C such that A intersection B is not phi, B intersection C is not phi, A intersection C is not phi, and A intersection B intersection C is phi. So we have to consider three sets. So suppose I am talking about A is the set 1, 2. We want A intersection B should not be phi. I am considering it as 2, 3. Suppose I write another element over there, 4. This is the set B. We are considering clearly A intersection B, it has a common element 2. It means A intersection B is not phi. B set we have constructed. Now B intersection C should not be phi. We are considering another set C. So that B intersection C and A intersection C both should not be phi. We have to include the elements of A as well as of B. I include the element 1 over here, and I include the element 3 over here, and suppose I include another element 5. So what we will have, A intersection B is not phi, B intersection C is not phi, A intersection C is not phi, it is not empty. Now if we calculate A intersection B intersection C, A intersection B intersection C means I want to find an X which belongs to A and X belongs to B and X belongs to C. So is there any element that belongs to all these three? No. It is 1, 2. 1 is not present over here. This term is there. 1 is not present over here. It means 1 cannot belong to the intersection of these three. If I am talking about 2, 2 is present in these two, but it is not present in this. I am talking about 4, same problem is there. So there is no element which belongs to all these three sets. So we are saying that A intersection B intersection C, that is equal to phi, but none of these sets it is empty. Next we have is express the following sets in the interval notation. Look at this set. It is X such that 1 is less than X is less than 4. This is 0, this is 1, this is 4. So 1 is less than X is less than 4 means 1 is excluded, 4 is excluded, and we are talking about all the points in between. Then we have 2 is less than equal to, suppose 2 is over here, 6 is over here. 2 is included, 6 is included, and all the points in between these two. So these are the two sets we are talking about. Now we are talking about the intersection of these two intervals. Intersection means we are talking about the region that is common to these two. So the common region we have 2 is included in both these. 4 is included in this region, in this set, but 4 is not included in this. If I am talking about the common portion, the numbers up to 4 they are included, they are common, but 4 is not present in this interval. So we will put the dot like this. This is the common portion, common region that we have. So the answer we obtain it is 2, 4, and it is closed at 2 and open at 4. So this is the intersection of these two intervals. Next, X such that X is greater than minus 2. This is minus 2, this is 3. X is greater than minus 2 means minus 2 is not included, and all points greater than minus 2 they are included. Second interval we have is X is greater than 3. in both these strict inequalities there, we are using both these points, -2 and 3, they are excluded. What is the common region? This is the common portion we obtain. 3 is not included and rest all the points are included. It means that the intersection of these two intervals, 3 is not included, all other points they are included. So the answer we obtain, it is 3 to infinity. This is the set we obtain. Next is, this interval is given. We are saying -2 is less than x is less than -1. -2, we have points like this, so we consider -2, -1, 2 and 3. -2 is less than x is -1. -2 is not included, -1 is not included. 2 is less than x is less than 3. 2 is not included. 3 is not included. So is there anything common in between these two? There is nothing common in between these two intervals. So we are saying that the answer of this intersection, it is 5. There is nothing common in between these two. Next is x such that 1 is less than x is less than 4. We are marking the points 1, 2, 4 and 6. 1 is less than x is less than 4. 1 is less than x is less than 4. Both the points they are excluded. 2 is less than equal to x. 2 is less than equal to x is less than equal to 6. We are talking about the union. Now, when we are considering the union, we are talking about the region that both these will cover. Together they will cover this. We start over here. 1 is not included. All the points after this they are included. 4 is not included, but it is included over here. So the 4 is covered in this region, this common portion. And finally 6 is already there. We have this point 6. This is the point 1. This is the point 6. So it is open at 1 and closed at 6. It is open at 1 and closed at 6. So this is the interval we are talking about. This is the region that we obtain. Next, x is greater than -2, union x is greater than 3. Now we have union over here. This is -2, this is 3, x is greater than -2, x is greater than 3. This is the region we are talking about. What is the region both these cover? We are not talking about the intersection, we are talking about the union. Union means either this region or included in both. So we obtain, this is the region we have, and the answer we obtain it is -2 comma infinity, and this bracket it is open from open at both the sides. It is the open interval -2 comma infinity. Next we have is the term difference of the sets. So suppose two sets A and B they are given to us. Then the difference between the two sets A and B, it is x, such that x belongs to A and x does not belong to B. Let us consider the Venn diagram. Two sets A and B are there. This is the universal set U. We are saying x belongs to A. We are talking about the elements of A, and x does not belong to B. X should not belong to B. It means when we are talking about A minus B, we are talking about the region of A which is not the part of B. only those elements of A which are not the part of B, that is the set A minus B. So what we are saying, that X belongs to A minus B, this thing means X belongs to A and X does not belong to B. That is all those elements of A which are not the elements of B. Let us consider an example now. We are talking about this remark first. We are saying A minus B, that is equal to A intersection B complement. So let us try to understand this first. We have to prove this thing, that A minus B, it is like this. So if we talk about the left hand side over here, A minus B I am talking about, it represents, this represents all elements of A which are not elements of B. And when I am talking about A intersection B complement, A intersection B complement, what is the definition we have? If an element X belongs to A intersection B complement, what is the definition we have? X belongs to A and X belongs to B complement. What is the definition we have? X belongs to A and X does not belong to B. Compare both these results. We are saying X belongs to A, all elements of A, and X does not belong to B, which are not the elements of B. So we are going to use this result very often. A minus B, whenever we have, we can write it in the form A intersection B complement. So you must remember this result, because this will be used when we are going to prove the results in our next chapters or next lectures. We will use this result. Next we have is an example. It says if A is equal to, this set is given, it has the elements, the set A is given, it has the elements, X is a factor of 6, natural numbers which are factor of 6, B has natural numbers which are factors of 8. A has elements, what are the factors of 6 natural numbers? 1, 2, 3, 6. What are the factors of 8? 1, 2, 4, 8. We have to find A union B. 1, 2, 3, 4, 6, 8. This is A union B. We have to find A intersection B. The common elements we have over here, they are 1 and 2. We have to calculate A minus B. A minus B means all the elements of A which are not in B. If I write elements of A and I exclude from this which are elements of B, 1 is there in B, I exclude this, 2 is there in B, I exclude this. The set I am left over here, it has 2 elements, 3 and 6. This is the answer for A minus B. When I am talking about B minus A, I am considering all the elements of the set B. I am removing from this set the elements of the set A. A has 1, A has 2, 4 is not present in A, 8 is not present in A. So we obtain that B minus A has 2 elements, 4, 8. So this is how we calculate A minus B and B minus A. A minus B means all those elements of A which are not present in B. B minus A means all those elements of B which are not present in A. Next we have is two sets are given. One is the set A. it has elements 1 by x such that x belongs to n and x is less than 8. We are talking about the elements we have over here. X is less than 8 and x is a natural number. Numbers 1 to 7 we are talking about. So elements we have over here, they are 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7. It is strictly less than 8, so it is only up to 1 by 7. And we are saying B has 1 by 2x, x belongs to n and x is less than equal to 4. It is less than, so we are considering up to 7. It is less than equal to, so we will have the numbers 1, 2, 3 and 4. These are possible values of x. Set B will have elements 1 by 2, then 1 by 4, then 1 by 6 and 1 by 8. These are the elements of the set B. What is A union B? It has the elements 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7 and 1 by 8. All the elements of A and B. What is A intersection B? The common elements we have over here. 1 is not common, 1 by 2 is common, 1 by 3 is not common, 1 by 4 is common, 1 by 6 is common. Next is A minus B. We are talking about the elements 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7. These are the elements of A. Remove from this set the elements of B. 1 by 2 is removed, 1 by 4 is removed, 1 by 6 is removed. So we are left with the set 1, 1 by 3, 1 by 5 and 1 by 7. When we are talking about B minus A, write the elements of B. 1 by 2, 1 by 4, 1 by 6, 1 by 8. Remove the elements from the set A. 1 by 2, then 1 by 6. We are left with 2 elements. 1 by 4 is also there in the set A. So we are left with only one element. So we are saying B minus A, it is the set having elements of B which are not in A. Next is an interesting set we are going to talk about. It is if R is the set of real numbers and Q is the set of rational numbers. What is R minus Q? We are removing all the rational numbers from real numbers. What we will be left with is irrational numbers. So, sometimes we say it like this, that the numbers, the real numbers which are not rational, they are irrational. This thing justifies it. You are saying, what are irrational numbers? They are real numbers which are not rational numbers. So we can say it like this, when we are defining R minus Q, we are talking about X such that X is a real number and X is not a rational number. A real number which is not a rational number is an irrational number. So R minus Q, it represents the set of irrational numbers. So sometimes we write irrational numbers as Q complement. It means it is R minus Q. From the universal set, we are removing the set of rational numbers. From the real number set, we are removing the set of rational numbers. Next we have is, if A and B are two sets such that A is a subset of B, then we have to find A union B, A intersection B and A minus B. Let us consider the Venn diagram, the easiest way for this. U, B, A is a subset of B. What is A union B? When we are talking about A union B, we are saying X such that X is in A or X is in B or both. X is in A or X is in B or both. we are saying X is in A, X is in B, or both, it means that we are talking about the set B. And we are taking the union, we are talking about the complete set. A intersection B means X such that X belongs to A and X belongs to B, the common region between these two. Larger circle, smaller circle, the common region we have is A. And what is A minus B? All those elements of A which are not element of B. Is there any element which is element of A but not the element of B? There is no such element. We are saying this set, it is empty set, it is the set phi that we have over. So these are the sets we are talking about. Next is now we are going to start with our next proof. We have to prove that A minus B, that is equal to A minus A intersection B. So if we look at the Venn diagram over here, we are saying this is the set U. We are talking about these are the sets A and B. A minus B means we are talking about those elements of A which are not the elements of B. I am talking about two cases over here. In the first case, I am directly plotting the region A minus B. A minus B, we are saying it is those elements of A which are not the elements of B. Now when we are plotting this part, we are saying A intersection B. We are talking about this region. This is A intersection B. And we are removing from A this portion. So we are saying either we are removing from A all the elements of B. This is equivalent to saying that we are removing from A. This is what we are left with. This is the part of A and this is the removed part over here, and this region we have obtained. This portion we are saying this is A minus A intersection B. So either we are removing B or we are saying we are removing those elements which are common between A and B. We are talking about the same thing. Next thing that we need to understand over here is that A is equal to A intersection B union A minus B. Again, let us plot the Venn diagram over here. We will see these results using Venn diagram. Proofs we will discuss in the next lectures. The region A intersection B. This is set A, this is set B, this is set U. This is set A, this is set B. What is A minus B? We are talking about this region. This is A minus B, this is set A and this is set B. What is the union of these two portions? What is the union of these two portions? We are saying that we are including this portion over here. Now what is the complete region that is shaded? It is the set A. So we are saying that the part that overlaps with B, which is A intersection B that we have over here, and the part of A that does not belong to B, which is A minus B over here. When we take the union of both these, we will obtain the complete set A over here. So we have this result that A is equal to A intersection B union A minus B. Next result that we have, it is A minus B union C. We have now three sets A, B and C. Let us try to understand these condition. When we are saying B union C, these are the sets we are saying A, B, C. B union C means we are talking about all the elements of B, all the elements of C, all the elements of C, and we have removed this portion from A, so we are left with this region. This is the region we are saying A minus B union C. Look at these two portions now. We are talking about this is A, B, C. A minus B means we are talking about this region of A. This is A, this is B, this is C. From A we have removed this portion. A minus C means we have A, B and C. This is A, this is B, this is C. From A we have removed the portion of C. We have removed the portion of C. This is representing A minus B. This is Venn diagram for A minus C. And what is intersection of these two? We are talking about what is intersection of these two. When we are saying A minus B, this region is there. A minus C, this region is there. And if we are talking about the intersection of these two, this is the common region we will obtain, and this is equal to this region that we have. So we can understand this result that A minus B union C. From A we have removed B union C, we are left with this portion only. We are left with this portion. Similarly, when we are saying A minus B, we are having this portion, A minus C, this portion. The common region between these two is A minus B union C. Next, suppose these are the sets given to us. One is the set A. It has elements 1, 2, 3, 4. B has elements 2, 3, 5, 6. C has elements 3, 4, 6, 7. We have to find A minus B intersection C. So, first of all, we calculate B intersection C. B intersection C means common elements between B and C. 2 is not common, 3 is common, 4, 5, 6 is common. B intersection C, we have it has elements 3 and 6. A has elements 1, 2, 3 and 4. We have to find A minus B intersection C. It means from A we have to remove the elements of B intersection C. We remove 3, 6 is already not there. So the answer we are left with is 1, 2 and 4. So we are left with these 3 elements 1, 2 and 4. This is the answer for A minus B intersection C. The next operation that we have over here related to sets that we have, it is the symmetric difference. We have seen union, we have seen intersection, we have seen difference. These were the 3 operations on 2 sets. We have seen complement. Now we have another operation, that is symmetric difference. It is denoted by A delta B, and by definition it is A minus B union B minus A. Let us try to understand what we mean to say by this operation. But the result we are getting, we are having the universal set. We have 2 sets A and B. What is A minus B? From A we have removed the portion of B. This is A minus B. What is B minus A? This region we are saying this is B minus A. From B we have removed the portion common with, the elements common with A. The union of both these is the symmetric difference. The union of A minus B and B minus A is the symmetric difference of A and B. So let us try to understand it with an example. Suppose two sets are given. One is the set A, it has elements A, B, C, D. B has elements B, D, F, G. We have to calculate A delta B, or the symmetric difference of A and B. The formula we have it is A minus B union B minus A. This is the formula we have for the symmetric difference. A minus B means write the elements of the set A, remove from this the elements of the set B. We have removed B, we have removed D. We are left with A comma C. This is A minus B. We are talking about union, then it is B minus A. Write the elements of B. It is B, D, F, G. From this set remove the elements of A. We are having A, B, C, D. So B is removed, C is removed, D is removed. This is the set A minus B. This is the set B minus A. What is union of these two sets? It is A, C, F, G. This is the symmetric difference that we have. If we use Venn diagram, we have sets A and B. The common elements over here, they are B and D. This B and D, they are common. A and C is over here. F and G is over here. These are the sets A and B. When we are talking about union, all the elements are there. When we are talking about intersection, B and D is there. When we are talking about symmetric difference, we are saying A, C, F and G. These are the four elements in the symmetric difference of A and B. Next we have is a set is given. Let n be the set of non-negative integers. It is given that n is set of non-negative integers. It means we are talking about n is the set of non-negative is natural numbers union 0. N is not natural number, it is non-negative. Non-negative means neutral element as well as the positive element. So n is natural numbers union 0. I is the set of integers. I, we are saying it is the set of integers. NP, the set of non-positive integers. NP is the set of non-positive integers. Non-positive means we are talking about the negative integers -1, -2, so on, as well as 0. This is the set NP that we have. And P is the set of NP is the set of non-positive integers. E is the set of even integers. E is the set of even integers. 2, 4. We are talking about the integer. Then when we are talking about this set E, it will include the negative numbers also. So we will have over here 2, 4, 6, so on. On negative side, it is 0, -2, -4, and so on. This is the set E that is given to us. And P is the set of prime numbers. P is given to be prime. Determine whether the following statements are true or false. So first is I minus n is equal to np. What is I? I is the set of integers. From the set of integers, we are removing n. From the set of integers, we have removed this. Consider over here. We are having integers like this. It is 0, 1, 2, -1, -2, -3. From this set, we have removed these two elements. We have removed 0. What we are left with is the negative integers. We are saying we are left with this np. Is this true? No. This is not true, because what we are left over here, what is n? The set we are left over here, it is -1, -2, and so on. This is not NP because we have element 0 over here. We have the element 0 over here. Second part. This is the first part. Now the second part we have is n intersection NP is equal to 5. We are talking about the set N. It is N union 0, that is all non negative integers, and we are taking the intersection with this set NP. We are talking about this intersection with NP. The answer we have the common element over here, it is the number 0. This set, it contains the number 0, it means that this is not an empty set, it means this statement is false. Next, E intersection P is 5. We are talking about the set E. It has the elements 0, 2, 4, so on, minus 2, minus 4, and so on. This is the set E. Prime P, if we are writing, they have elements 2, 3, 5, so on. If we will take the intersection E intersection P, the common element we have over here, it is the number 2, that is common over here. So again, this is not equal to 5. It means this statement is also false. Last part we have is N delta NP, symmetric difference of N delta NP. It means we are talking about N minus NP union NP minus N. This is by the definition we are saying. And we have to prove that this is equal to I minus 0. What is N minus NP? N is, if we are writing the set N, we are talking about 0, 1, 2, 3, and so on. From N, if we remove all the elements of NP, only element common over here, it is 0. For this set I am talking about, what we are left with is 1, 2, 3, and so on. When I am talking about the set NP and I am removing the elements of N, I am taking union. What we are left over here? The only common element is 0. 0 is removed over here. We were left with minus 2, minus 1. If we will take the union of these two sets, we will obtain so on up to minus 2, minus 1, 1, 2, 3, and so on. We are left with this. We can write this set as so on up to minus 2, minus 1, 0, 1, 2, 3. And from this set, we are saying only 0 is there, which is not over here. We are having this set. If I write minus 0, it means I am removing this element 0. It is equivalent to this. What is this? This is the set of all integers I, and we are removing from it the element 0. So what we obtain is that the symmetric difference of N and NP, that is equal to set of integers except for the number 0. So it means that this statement is true. So this was all about the operations: complement, union, intersection, difference, and symmetric difference. So we have listed certain problems over here that you can try. So this is the exercise part. You can try these questions at your So you must try these questions, and if you face any problem with these questions, these are provided in your sheets. So if you face any problem related to these, then we can discuss them in the doubt session.